Good morning, and thank you for joining me in my shop here. It's April 6th today. Looks like a nice sunny day here. Looks like spring maybe is coming, and maybe the snow is done with us. I'm pretty hopeful for that. Tomorrow is the big eclipse. The full darkness eclipse is about a 2.5 hour drive away from here. I don't think we're going to do it, even though it would be neat. It's too much for a few minutes of darkness. I think if I just wait till late in the day, the sun actually goes down and it gets dark. Kind of the same thing, sort of. But anyway, the weather's going to be bad tomorrow. That's unfortunately the situation, including down around Buffalo and the North Shore of Lake Erie in Canada, where you're going to have total darkness. I think the weather's going to be bad. Don't say that. Okay, what's up with this radio? Well, someone else has done the restoration work on it some time ago. Don't know who. Don't know if it ever worked. We could assume it did work after that. I've played it. It's not receiving anything. It's insensitive to inputs into here. Barely sensitive to an input into here, a finger input. I've tested the tubes, including the rectifier tube. Yesterday on video I tested these 4, and I did not test the rectifier. I did that afterwards anyway, just to be sure there's nothing wrong with the rectifier. Nothing wrong with any of the tubes. So radio not working, tubes are good, somebody else did work on it. So there's a couple possibilities here. One is it's just suffered another typical old age failure, a capacitor, a resistor, or something like that. And that can be found through a little bit of troubleshooting, and hopefully that's where I'll end up with this. Or another possibility is the fellow who did the work made a mistake and could never figure out what had gone wrong, and so the radio's sitting here not working because the last fellow made a mistake. I don't think that's terribly likely. The work was done very carefully in this radio by whoever did it, so I just can't imagine that that's the case. So how to go forward from here? I would like to know where the fault is or failure in the radio. I'm just assuming there's one. It could be more than one thing has gone wrong in here. But before troubleshooting, I think it might be good to spend some time studying the schematic and getting familiar with the circuitry in this radio. I think also on the video I may have barked out, look, it's only got one IF transformer. The other IF transformer is tucked away underneath the chassis. So that's where that is. And these resistors, so when we look, resistors that are paralleling the two lights, when we look at the schematic, maybe we'll even start right there. You'll see there are 2 resistors shown on the schematic. The interesting thing about this is there's 2 lights. Typically with a 5-tube radio, my experience is there's only one light, and it's drawn from, the power is drawn from the filament of the rectifier tube, and it's really designed for one light bulb, and in fact one type of light bulb, usually a 47. This one's got 2 light bulbs with resistors across them, so I'm just a little I'm wondering how they're doing that in this radio. So I think the next stop is the schematic, and we'll spend 5 or 10 minutes going through it here. Okay, here's the schematic for the radio, and let's check out those light bulbs right away, because there's something. So here they are, 2 of them shown here. There's the resistors, R13 and 14, and oh, where's the heater? They're not showing the heater. The heater's down here. There's the heater, and they show it with a tap. They're not showing anything connected to the tap. How are they powering these lights? Oh, wait a minute. The lights are in series. Looks like they're powering the lights as just another element in series with the heaters. That's a little unusual. I don't think I've seen that before. And obviously, if a light bulb should burn out and you didn't have this resistor, then the radio would stop completely. because these would be in series. So light bulbs burn out regularly, tubes don't burn out regularly. So to compensate for that possibility, they stuck resistors here. And the combination of the bulbs and the resistors, and look, there's another resistor here, must be responsible for dropping excess voltage. So if we come through here, oh, this is interesting. These are 6-volt tubes here. So typically in a 5-tube radio you have 3 12-volt tubes, and then a 25-volt and a 50-volt, something like that. And if you add up all those numbers, it comes to around 115, 120. If we add these up, 6, 6, and 6, that's about 20. So there are about 45, 55, 65, 70. So this is only 70 volts dropping here, but it's plugged into a 120 volt line. So you got to get rid of 50 volts. So some of it is dropping here, but it's going to be in the realm of 10 or 12 volts here. So you're dropping quite a bit on this R12. This must be a big resistor. I'll bet you this is the one. I think we got a glimpse of one stuck on the side of the radio chassis. I think we got I think that's probably where that is. So that's an extremely unusual, at least from my experience, a very unusual way of feeding pilot lights. When you first turn on the radio, all these heaters are cold, and then the filaments and the lights are cold. Everything's cold, so there'd be a rush of current for some duration, perhaps a fraction of a second. During that time, these guys can get beat up pretty hard. In other words, they can turn the radio on. These will flash brightly, and then I've seen them. They dull down, and they this is a little tricky for me to figure out. Is this got a cathode? Is this a cathode tube? It is. It has cathodes. Okay, not so difficult. I thought there might be actual current flow off the heater element here. There'd be no cathode in this tube, and then you'd have plate current flowing in these too in some way, perhaps. I don't know. Some of these lights conduct plate current, but not. I don't think these ones do in this radio. I think they're quite separate, really, from what's going on here. You could pull this tube out, and these guys would stay on. They wouldn't do anything, I don't think. On the safety side, if you pull one of these tubes out, let's say you pull this one out, and you take a voltmeter and stick it in where the heater contacts are made, you're going to read a high voltage there. You're not going to read 25 volts. You're probably going to read 120 or 110, pretty much everything that's coming in on the plug. Because you've created a voltage divider with the meter being one of the elements in the voltage divider by hooking it up here. And of course it's 10 million ohms and everything else is 4 ohms. So all the voltage drops on the meter. You're going to get a big reading on it. And so likewise, if you were to stick your fingers in here, like pull this tube out and stick your fingers on there, you'd know it for sure. You'd get a shock. What about these lights here? So let's say a light burns out. Well, you still have the resistor here, so there's no open circuit and there's no high voltage sitting here. You know, if they didn't put these resistors here, and maybe they picked lights that can do the job without the resistors, and then one of these light bulbs burned out, you'd have 120 volts sitting across it. And you're sticking your fingers in there, clumsily trying to change this light. Wham! You're going to get, they're going to get a shock here, assuming you've left the switch on and you're stupid. You have to be a little stupid. I was just a little stupid. Wow. And the whole time you'd be sticking your fingers in here thinking, well, there's nothing here, and only 6 volts from the heater tap or 6 volts from a transformer. But in fact, if they didn't have these resistors, you can get killed. And the light is an invitation. Stick your fingers right there. Okay, so that's got to be why these resistors are here. They're actually a safety feature. interesting. What are the, so we can read the value of these. So why don't we do that? Let's R12, 13, and 14. What are the values of those guys? I think we're going to find it on this other page. Page of super writing. There's a ton of writing in here. So it was 13, 14. These are, well, no. R. 12, 13, 14. So 13, 14. 80 ohm tapped wire wound metal clad resistor. What? An 80 ohm tapped wire wound metal clad resistor. R13 is 40, R14 is 40. So I think the resistors we're seeing, which look like they were obviously installed by the guy who did the work on the radio, the ones that are installed right on the light, are a replacement for this thing. This 80 ohm tapped wire wound metal clad resistor. Oh, so what happened with this? We don't know. In R12, this is the 15 watt resistor wire and line cord. So we got something quite unusual here. I've almost never come across. The challenge here in the radio is to dump a bunch of power off that the tubes don't need in the heaters. So you have a resistor, kind of like a fake tube if you like, in series with the rest, and its job is to drop the rest of the voltage, and in doing that it's bound to dissipate a lot of heat. So you have a 15 watt. That's a lot. 15 watts to keep your cup of coffee quite warm. 15 watt resistor wire in line cord. So the original cord has been replaced, and this 15 watt resistor is missing now, unless something has been done. Some kind of resistor has been installed in place of it. The reason they use the resistor wire, which sounds like a stupid idea, and I think it is a stupid idea. Now, whoever thought this up, well, he's long been buried, but nevertheless, this is a dumb idea, because that power cord, you could coil it up, stick it under a pillow, and burn your house down with it. This is a crazy idea. The line cord gets warm on this radio. It's dumping 15 watts. But not the one that's on the radio anymore. Well, this is a big finding. This is a big finding. Now, if you take away this resistor, I think you're in big trouble here. You have to have a resistor in there somewhere. Otherwise, you're going to overpower the heater voltages, and the current flow through the tube is going to be too high. Even the current flow through the light bulbs is going to be too high, or higher than intended. So what has the guy done? I don't know what he's done. We're going to have to look into this carefully though, because if this hasn't been handled properly, then all those tubes, instead of running with 6 volts, are running with 8 volts. That's a big difference, 6 and 8. Oh my gosh, wow, lots of stuff here to read, but I'm not going to read it right now. I had no idea that those lights were going to lead to this kind of discussion. Wow. Okay, we'll keep all that in mind. Now, let's just run through the... I was going to spend 5 or 10 minutes on it. I already did, and I haven't even gone through the schematic yet. So here we go. Let's go through the schematic. So we have, starting at the speaker end, we have the speaker and output transformer, and the output transformer's input signal is the output of this tube. There's the plate. This comes down to the power supply. Only this part of the power supply is utilized. They don't utilize this part here. So the same amount of filtering on the B+ throughout the radio. This capacitor is to quell harmonics that might be generated by these tubes. This is a tone control. That's the switch on the back of the radio kicking in or disconnecting a capacitor. And the capacitor is robbing the output transformer of some treble tones, some high tones, high pitched tones. That's how that's working. This is the cathode. Cathode is grounded to the chassis, or B minus. We don't know yet. I haven't studied that. Whoops, I should have studied that. We'll look at that in a sec. We'll look at that when I'm done. So we don't know what this is, either to a B minus wire or right to the chassis. Usually these things indicate right onto the chassis, but not necessarily. So this is the cathode resistor generating bias for the tube, cathode bias on the tube. Here we have the output from the detector tube. This is audio going through this blocking capacitor. We're going to need to check, probably check them all. This is probably a little guy here. What's it doing there? Don't really know for sure, but once again, maybe quelling harmonics or something like that. Not sure. Go back here. Okay, so this is the triode part of this tube, and this is the detector diode part. And they've drawn the tube in such a way that it's kind of positioned in the circuit it's working with. This is the cathode. The cathode's working for both the triode and the diodes back this way. Same cathode. One cathode, I'm pretty sure. So this is the audio amplifier. It's getting its audio signal. There's a grid cap drawn right there. It's getting its audio signal from the volume control right here, potentiometer. This is blocking a little bit of DC that might get through from the detector action. And this is probably a very large resistor here. And this is basically biasing itself, the self-biasing arrangement here. So the negative voltage that will develop on the grid is from the tube operation itself. There's no external application of a bias. This is also probably getting rid of harmonics or high-pitched frequencies that we really don't want. And there's two diodes. One is doing the audio work. The other one is supplying AVC control voltage in a little bit of a complicated circuit here. So the voltage from this diode is being fed through this coil onto the grid here. So as this voltage goes up and down, or down and down, this is a negative voltage here, it will cause the negative voltage to be applied to the grid. So we're getting some kind of signal grounding arranged here, but not a DC grounding. So this DC voltage doesn't get grounded down, but look, it's shared out into here, which is going to go to the grid of this tube. The signal grid, not the oscillator grid, on the grid cap. So that's the AVC system. The DC voltage on these grids is dependent upon the strength of the signal. Stronger the signal, greater the DC voltage, and the less amplification these tubes will do. So it's like a governor, like a mechanical governor, if you like. So that keeps the output volume level as you tune between weak and strong stations. That's the concept behind it. And unfortunately, when you tune between stations, when there's no signal for the radio to pick up, it cranks these tubes right up, and you hear the rush of white noise coming in from the antenna and the atmosphere and everything else. So that's why these radios are so noisy between stations. I used to think as you tune the station in, the station's knocking away the noise. But that's not what's happening. When you tune in the station, the radio is turning its own volume down. That's what's happening. So we have an IF transformer here, IF transformer here, in between the IF amplifier tube sitting here. IF stands for intermediate frequency, and it's the main trick in these radios, where you have to do a little tuning out here. This part's all fixed at one frequency, and the frequency is it written on here? There it is, 456 kilocycles, or kilohertz, 456. And then These transformers are conveying the signal from one stage to another without conveying the DC voltage that's operating this stage and would interfere with what's next. And the same thing here, they use a transformer. I see here they're using a capacitor to stop the DC. Here they're using transformers to stop the DC from flowing right on through. These are tuned very carefully. All tuned circuits, but tuned to the frequency we saw down here. The result of that is the radio's gain is very, very good. Its selectivity is very, very good. Now, how is it you tune in 680 out here, 680 AM, and somehow in the middle of the radio that signal has become 455 going through here? If it's not 455 kilocycles, it doesn't go through. Just like a radio that can, whoops, this part of the radio can only hear one channel, 456 kilohertz. So you have to change what's coming in on the antenna to 456, and then it'll shoot through the radio. So the way that's done is a bit of a trick. This part of the radio is an oscillator, so this is making a tone. It's actually making a radio frequency signal. Roughly 456 kilohertz above the AM band, roughly, because the AM band covers a range of frequencies. So does this. This will range when you tune the radio. When you tune the radio, you're tuning this coil, this system, I should say, the local oscillator, and you're varying its frequency. So for instance, to make the numbers easy to understand, if you wanted to tune in 1 million, let's say there's a station at 1 million. Here in where area I'm in, there's a strong station at 1010, just above 1 million. But let's say you pick 1 million. So you tune in the station, the signal's coming in, it's passing through this transformer, it's coming over along here at 1 million hertz, and it's on this grid. It's 1 million hertz going on this grid, and this tube's going to amplify it, and now there's 1 million hertz coming out of here, the signal you want to listen to, but this is tuned for 456, not 1 million. And what this looks like to the million is a short circuit. This looks just like nothing. Like, boom, it's gone. The million can't make it. So what do? So if you introduce another frequency, another oscillator frequency from this circuit here into this tube, you can mix the two together and a little bit of magic happens. The magic is you end up with not only this signal coming out of the tube, the original million, and the local oscillator signal, which you don't want, but it does come out of the tube. It would be 1 million plus 456 if the radio were tuned to 1 million hertz. So local oscillator running at 1,456,000 hertz. That signal is stuck on this grid. So inside this tube we have two signals now. We have the signal from the antenna at 1 million. It's 1 million because we've tuned it, and we're selecting the 1 million signal. Meanwhile, the local oscillator is serving up its own signal from down here, and it's at 1,456,000. Why is that? The radio's been designed that way, so that when this is tuned to 1 million, this is tuned 456 kilohertz above. It's built that way. That's why it's happening. Tune up a little bit, this will go up in frequency along with it. So now you got these two signals in this tube. You have a single electron flow through it. There's a couple of different ways of visualizing or understanding what's taking place in the tube. But the easiest one is to say, look, there's electron flow through here. This grid is affecting the flow, and this grid is also affecting the flow, and with the two of them affecting the flow, you get this mixing taking place. Now another way of looking at it is this is operated in a non-linear way. A non-linear amplifier will generate harmonics and stuff like that. And if you put these two signals into a non-linear operating tube, you'll get them to mix. And mixing means you're going to get the two original signals, the million and the 1.456 million, and two more signals. The addition of those two, so if you add 1 million to 1.46 million, you get 2.46 million. So there's a signal here, 2.46. But there's no chance of it going any further in the radio because the radio's tuned to that 456 from here on. The other signal you get is the difference. It's kind of a, if you've never heard this before, you might have trouble believing it. But if you subtract the difference between the two frequencies, so it's 1,000,000 and 1,000,456, you end up with 456, the magic frequency. So coming on this plate of this tube are 4 signals coming out. The 2 originals going in, the sum of the 2, and the difference of the 2. And the difference of the 2 happens to be 456. Look, it doesn't happen to be. Everything is designed for this to happen. So with this running at 1.456 million, a 1,000,000 hertz signal on the antenna is converted to 456. And that particular frequency, the radio is sensitive to, and shoom, away it goes and out the speaker. You hear it coming out the speaker. So this is the whole trick of these radios. They're called Superheterodyne radios. The super part means above your hearing. You can't hear this. The frequencies being mixed in here are radio frequencies. You can't hear them. They're way too high. Super. The heterodyne is a fancy word for the mixing. You heterodyne 2 signals, they mix together and you get products coming out. Signal products coming out. Superheterodyne. The benefit of this is these circuits, which have to only be operating at one frequency, can be built very, very specifically, very carefully to maximize the utility of this part of the radio. If you didn't do this, then as you tune, from 1,000,000 to 1010, you'd have to tune everything here. Everything would have to be tuned along, and they'd all have to line up perfectly. That's tricky business. These early 1920s radios were like that. They're called tuned radio frequency, and they don't have the superheterodyne technique in them, and instead the radio operates at its tuned frequency all the way through to the detector. And the result of that is a number of tuned stages, and they all have to tune absolutely precisely and track along perfectly. And often you look at these old radios from the 1920s, and you'll see what looks like the same thing repeated in them. You'll see a capacitor with 4 sections. It all looks absolutely identical. They are absolutely identical, so they'll work the same, they'll track the same as you tune through the band. This was the solution to that. This eliminated the need to have many tuned circuits tracking perfectly. You just have to make this guy track with this guy. That's all you got to do. So when you tune 1,000,000, this thing is actually oscillating at 1,000,000 plus the IF frequency, and then the difference will be just right to go through the radio. So that's the whole deal here with these radios. They start out with what you're actually tuning, they convert it to an intermediate frequency, and then at the end they detect it, which means they rectify it, and the action of rectifying it reveals the audio or makes the audio signal accessible, or you can work with it however you want to put it, and then from here on in it's audio out this way. So that's the story here. Now we got to look at this power supply again. So I see the capacitors are shown. Well, we'll look in the radio and see, is this a wire that's running between all these symbols, or is this an actual connection to the chassis? Now it's important to figure this out. Let's follow it in from here. So any connection to the chassis showing up, well, yeah, these lights, they are in a socket, and the socket is attached right to the chassis, isn't it? It may not be. It may not be. We'll have to look more closely at this. So here's a symbol. That looks like that would be to the chassis. This capacitor's job would be to drain out any unwanted signals that might be in here. And drain out, I'm using the word drain out. They don't really drain anywhere. Nothing drains. But you can think of it that way. So this is a curious thing, this whole thing. Wow, like if you didn't realize what's going on here, you're setting yourself up for some surprises. That's for sure. Certainly the first thing I thought is the lights are fed from a heater tap. Wow. We want to find the R12 and we want to examine these lights. Let's just stay on this right now. We can even look at the base of the 25Z5 and see what's happened. This is probably a pin, and my guess is, based on this diagram, there's nothing connected to it. But this will be a terminal on the tube socket, in case you wanted to use it. Okay, let's examine this. Maybe we might even be able to find this. We'll see how many things we can find soldered. We can find this, the end of these. This is easy to find. Okay, we'll stick in the power supply and the light bulb area. Okay. Now I've done hundreds of radios, and every radio is a new journey. And there's just, it's surprising to me how similar and yet different the experience is in trying to work on these guys. So here's the lights I'm talking about. Here's the resistor. Now this is a replacement. We don't know the value of it. Assumably the guy used the schematic, but we don't know what he's done. If you look at these sockets very carefully, and I think I'm going to bring up the other light here, the other camera. Apologize for the autofocus. So, having grabbed the camera, I've now forgot what I was going to look at. Oh yeah. So this. Just waiting for it to focus up. So this socket, the light bulb is using for a contact to get electricity. You can see that this is soldered to it too. So this part is part of the circuit, and then the other part is back here. So, but if you look at how it's supported, how is the light supported? I'm going to fix the focus here, or we're just going to go nuts. Let me just bear with me a second here. What I'm doing, what I've done so many times, I'm calling up the dialog box because I couldn't think far enough ahead when I started the video. There. Okay, so it won't act up anymore. Isn't that beautiful, eh? Like, that's just fantastic looking. So back to the light. So we're looking at the bracket. The bracket is attached to the chassis with the screw there. So the bracket is part of the chassis. Now, does the bracket touch this part of the socket? And the answer is no. If you look right in here, you'll see insulation. You see how the bracket is bent up, comes up, and then on either side, it's like a sandwich. On either side are some non-conducting cardboardish materials, a little like cardboard stuck in there. So this bracket is not touching the socket. Well, what that would mean is if you did this while the radio's operating, you might feel it. If the light were burned out and you did this, you might feel it, but there's a resistor there. If the resistor was not there and the light was burned out and you stuck your fingers in here and you left the radio plugged in and you had it turned on and you're stupid as a bag of nails at that point, actually a bag of hammers, even stupider, you're going to get a shock off that. And then you're going to wonder, how can that give me a shock? Yeah. Okay, so that's the story there. Now there's another resistor we need to find, and that is the dropping resistor. The heater dropping resistor. And this is a really difficult radio to look in. Go this way. How am I ever going to spot it? Oh my gosh, that's going to be tough. So there's a wire coming from the light here, and it's going to a terminal on the rectifier tube, which is to be expected, and it's all way up there. Oh my gosh, no way. I'm not going to see up in there. Ooh. And then looking back here, this is really, hats off to the guy who worked on this before me. Stuck capacitors up in here. Now, I did mention these capacitors which you left in, and these could be bad guys. There's two of them, I think. So you see some action over here. There's a rivet here. Inside is some terminals, and I can see a resistor here, looking kind of rough. And there's another connection made to the chassis. It's coming over to the tube socket. Okay, I have the feeling, look at these big blobs of solder here. This is the base of a coil right in here. Wow, this is like looking at a car radio. So there's that resistor that's mounted down on the chassis, and that's possibly the one we're supposed to look at. And what, you know what? I gotta get the little camera going in there, because I'm not sure what I'm seeing way up in there. So that's the resistor that's mounted on the chassis because it gets very hot. This is a high wattage resistor. It's got 3 terminals coming out of it. The one I saw on the schematic may not be this one. The one I'm looking for may not be this one. But I see a diode right there. Yeah, what is that doing there? Sure looks like a diode. Is it a diode? Under the rectifier tube. Ah. Let's go down this way. See, the last guy who worked on this radio, he's too smart. He's too smart. He's doing stuff. So there it is. What's it doing there? So that's a silicon diode, I'm pretty darn sure. I don't think I could be wrong about that. And let's see if I can just sharpen the focus on that. Whoops. There's no question that's a diode. It's hooked up to the resistor there. There's another view of the resistor. And there's no hope that that's original. Those parts didn't exist when this radio was made. Why would somebody put a diode? So the easy answer to that is, oh, they replaced the rectifier tube with a diode. That's possible. It can be done. It's not the simplest thing. But then you wouldn't have the rectifier tube in the radio. Huh. Well, what other things has this guy done? What has he done? He's done all kinds of stuff here. You want to see another one of those super connections? Here's a look at that. Oh, is that the one we looked at the other day? My God, you could put 20 amps down that little connection there. There's a theory about making joints. We can call that a joint. In the power system world, where I used to be, with 2,000 kilometers of big power cable, 3-conductor, 3-phase power cable under the streets. Each length can only be up to about 100 meters long. So you have a manhole. Every 100 meters you have a manhole. You're pulling in this piece of cable. Then you're making a splice in every manhole. A manhole is a splicing place where you splice together cable, or joint. That's the word that's used in the power industry. You join the cable. Joiners. And they make joints. Yeah, like joints. Yeah, joints. The principle that was set upon in the early days when these cables were first being made and everything was highly unreliable in the early days, like in the like 1910, in that range. There's still an awful lot of experimenting going on. The suspended insulator hadn't been invented yet. What? Yeah. Huh? So the principle that cable splices were built on was that if you were to overload the cable would blow before the splice. And the theory behind this was If you did it like that, you'd end up building a really, really rugged electrical distribution system. If you did the opposite, if you weren't careful and you just made the splices, good enough to do the job that they have to do, then in times of extraordinary stress, cable failures, short circuits, high load, whatever, errors in switching, whatever it might be, then you could damage the cable at every joint very quickly. Every splice would get ruined because it would overheat very quickly, and you destroy. You could do like $1 million worth of damage in a couple hours. So the theory is make the splices stronger than the cable itself, and that's what I witnessed when I was at Toronto Hydro. The cable splices were, yeah. There's no heat building up in those cable splices. They ran a little bit cooler than the cable itself. I don't know if that's true or not, but okay, enough talk about that. What to do about this? So now I've identified a circuit change. It raises a lot of questions about the fellow who did this work and what other things, clever, smart things he might have done that I need to figure out before I do something that will be stupid, such as do something. That diode is actually really setting off alarm bells. We're going to have to know what that diode is in there for and what's going on with it. So I've got to first figure out where it is in the circuit. So we saw it's connected to one end of this mounted resistor here. And where does the other end of that resistor go? Oh my gosh, this is going to be tricky to see this. The wires are coming up to the light. Wires are coming up to the light. Now isn't that similar to the schematic? The high wattage resistor. This can't be another resistor. This has to be the high wattage resistor because we're talking about 15 watts. A 15 watt resistor on its own would look like, and I'm not going to be able to grab one really quick. Let's grab one. I got one here. Here's some biggies. Let's take a look. 10 ohms. The wattage not written on it. Oh, look at that. It's been scraped clear so you can slide something over the windings. That you can look right in the... who did this? Where did I get this from? I don't even know. Maybe he scratched off the wattage. This is a high wattage resistor. Let's see if this one really shows it here. And again, scratched off. Clarostat, no value. It's not going well. Here we are. 10 watts. Look at this thing. 10 watts. It's about the size of the radio. And they're going to try to dissipate 15 watts. So this one's trying to do it all on its own. It's hollow, so air can go through a little bit. But they've taken that resistor and strapped it onto the chassis. So the chassis will carry the heat away. And then the temperature won't rise up so high because the heat is flowing away. 15 watts. Did I read that right? I read that wrong. Or did I just make that up? Maybe I made that up. And then the other side of the diode is attached to a terminal on the rectifier tube. Can I count or figure out what terminal that is? Good question. Take my half-dead flashlight here. Half dead or half alive? And I had a hard time soldering in there, I think. So that would be, how do you count these pins? Oh my gosh, so this is right. So I have to identify the two fat pins. I think those are them. If that'd be the case. That'd be pin 1. Looks like 2. Looks like pin 2. Pin 2. Looks like pin 2. On a 25 Z5. I don't think I have any of these either. I think this is a bit of a rare tube. Here's the 25Z5. 25Z5 has no tap on the heater. It has two cathodes. Vacuum rectifier doubler. So I think it's this one. I think it's a plate, if I've done this right. So it would be one of the two plates. Let's look at the schematic here. One of the two plates. Rectifier. So here we are. So here's so look what they've done. They've just so this is a full wave rectifier, and they've just tied it together and turned it into a half wave rectifier here. So they're kind of abusing this tube. Not really, but and what did I find? I found a diode attached. Well, this resistor is not really, it's not attached directly to the tube. Well, this is going to be difficult for me to sort out. What is a diode doing in here? You might think, oh, you just put it right across here. Maybe they did. But I tested this tube. It's good. There's nothing wrong here. Help me. What? Who stuck a diode in there? What were they thinking? What were they thinking? I have to figure out where that diode is in the circuit. It's the only hope. And to increase hope, I'm going to drink some coffee. Yeah, this is going to take some time, all right. First of all, the guy who drew this, he drew the lights in this weird way. Well, I redrew this when it's just simply the two lights in series, and each one has a resistor across it. Resistor 13 and resistor 14. Now when I read the description of resistor 13 and 14, it describes it as a wire wound metal clad resistor. Well, what do you think we're seeing when we see that piece in there that's tied to the chassis? That's a wire wound metal clad resistor. If I look closely at it, the resistor looks something like this. It's got three taps on it, and the distance between them is exactly the same. Now, a lot of these resistors, they look like this. They have a tap here, a tap here, a tap here, and one way out here. And this distance represents the amount of resistance. So if this is the same, the resistance is the same. This is R1314. This thing that's in the chassis is these two resistors. These two resistors. What's happened? They're still wired in, and now there's resistors up here, up on the line. So I'm starting to develop a theory here that the last guy made a boo-boo, failed to understand what this resistor was here, and consequently he did things which may not make sense. This is a non-working radio. Now we are down on the power supply. It's not likely any of this would stop the radio from working unless there's no B plus being generated because of the foolishness that took place in here. The diode, you can see I drew it in briefly right across the tube. I thought that's what it was for a moment, but then when I looked more closely, it looks like, and I haven't drawn it in, the diode is connected from here down to the old resistor. What? I don't know what's going on. So I still don't know what's going on. Why he's put this diode in there? And did he mess this up? Or is the high wattage wire wound resistor open? And this was his way around it, which is actually a more likely story. That he did understand everything, but there's a problem with the wire wound resistor. These resistors are pretty rugged, but you know, if you're dissipating 10 watts, they're getting hot. A lot of expansion and contraction and working of the metal, maybe it's failed. So I gotta stick an ohm meter on it. And the resistance, what's the frequency, Kenneth? The value of the resistance here is 80 ohm tapped. Well, there, see right there, tapped, wire wound tapped, 40 and 40. Okay, let's get out the ohm meter and see what's going on here. First, let's take a look and see what we can find out about the resistors that are up on top here. Ohms are probably reading the filament of the tube, of the light bulb. Wow. How about this one? No, we'll continue with this. Holy smokes! Yeah, I'm groaning a lot, but you know. Oh my gosh. I'm going to have to run the risk here of run the risk of what? When I use these pliers, I run the risk of snapping them on my finger. See how tight it is in here? These are dangerous pliers because you're working away with them and your finger might end up like this. And then the thing you're squeezing pops out and you go like that. That's why you never see me using those pliers. They are finger biters. I'll have to compare them to my other pliers when I eventually find them. Okay, so I've got the light out. What do we see now for a resistance here? 67 ohms. I have no idea what this guy's done here. If this is the right thing in any way. 67 ohms doesn't sound right. 40 is what it was supposed to be. What? I mean, this guy could be a genius. This is a 44. Probably calling for a 47. Let me look in the parts list here. Because if you pick a different bulb, it'll try to draw a different current, and in this kind of situation, maybe that's significant. Let's look again at the schematic here. So in the parts list, it may list the light bulb. Light 1. No, that's a L. Coil 1. I need light bulb showing up in here. Down here. Line cord with built-in resistor. Oh boy. Gee, did he turn that 15 watt resistor that was intended for the light bulbs, did he turn it into the line cord resistor? Did he do that? And then he put alternate. Here's his Mazda 44 right here. So it does have the right kind of bulb in it, a 250 milliamp bulb. Line cord with built-in resistor. Yeah, these were really bad actors. These things ran warm, and the insulation in them got damaged, and these are just really bad. And look, they cost you 90 cents. Oh my gosh, they're expensive. What's the most expensive part in the radio? $3.50 for the 2-gang variable condenser. $1.50 for the electrolytic condensers. $4.85 for the speaker. Oh my gosh, almost $5. Whew. That's deadly. Okay, how I gotta think about this a little bit. I think because I sort of have a theory now, a couple theories of what has happened here, and they're just ideas. I don't really know what's happened. I don't know what's happened. Yeah, kind of going through life. What happened? I don't know what happened here. What's happening? Well, I'm gonna leave it at that right now. I think for today. It's a beautiful sunny day outside. The weather's warming up a bit. I can poke my camera out here briefly. I can see the sunshine out there blasting through my window. Look at that. It looks like some kind of nuclear radiation outside, but it's not. It is. It is nuclear radiation from the sun. Yeah. Okay. That's it. I will pursue this situation further tomorrow. Try to resolve what the person's intention was, why they did this, what they were trying to achieve. And yeah, wow, interesting. All these radios are interesting, I find. Thanks a lot for watching, and see you tomorrow.